Right, folks, in this video, we are going to deal with collisions and the law of conservation of momentum. The first situation we're going to take a look at here is where two objects stick together. This is also sometimes referred to as a perfectly inelastic collision, meaning that kinetic energy is definitely not conserved and the objects stick together. So in this particular case, we have a van and a car colliding head on. So what's that going to look like? Well, beforehand, we have van, nice looking van, right? And we have car, a little bit smaller, moving toward each other. I like drawing pictures for these types of problems quite a lot because it helps to understand exactly what's going on in terms of the directions of the various velocities and momentums, but also just how the objects are going to interact with one another and how that affects the equation that we're going to use eventually. When they collide, there's a big blob mess of car and van stuck together, and we're trying to figure out how they are going to move after that collision. So how do we approach this? Well, when we're dealing with collisions, we're going to start with our basic conservation of momentum equation. So I'm going to say that the momentum of the van plus the momentum of the car, keep in mind that this is all prior to the collision, so I'm going to say initial, is equal to the momentum of the van after, a little apostrophe means that that velocity is the final velocity, plus the momentum of the car afterwards. Once again, the apostrophe means after. So since these two velocities are both after the collision, that means these two momentums, or momenta, are from after the collision. So that sum there is the total momentum afterwards. And based on the law of conservation of momentum, we know that the total before is equal to the total afterwards. Now, in this particular case, I know that the two objects become entangled after the collision. So they are going to be basically combined into one object. So what I'm going to do here is I'm going to just say mass total, velocity total afterward. I'm going to think of them as one object with their individual masses combined. And I'm going to go ahead and fill in that mass right now and say that that is, of course, 2,000 kilograms. And this velocity is our unknown in this particular problem. On the left-hand side, all I'm going to do is I'm going to plug in all of my various values, and I'm going to make a mistake. I just want you guys to know that ahead of time. But I'm doing it on purpose, which is better than doing it by accident and claiming that I did it on purpose. So 1,200 kilograms. This one is moving at 20 meters per second, plus the car, 800 kilograms. It's moving at 15 meters per second. All right, so what is the mistake that I made? Well, hopefully you guessed it, and you realized that this did say that the car was moving in the opposite direction of the van. Likewise, it was a head-on collision, so they're definitely moving in opposite directions. So what I'm going to do is I'm going to make the velocity of my car here negative. All right? Doesn't matter which one you make negative, as long as they are of opposite sign, because they are, of course, of opposite direction as well. Well, from here, there's nothing left but the algebra. So what am I going to do here? Well, this value, 12,000 times 20, or sorry, 1,200 times 20 is 24,000. 800 times negative 15 is negative 12,000. On the right-hand side, 2,000 kilograms, still times this unknown velocity. I combine the two on the left, and I get 12,000. I've been lazy, though, in the previous step and didn't use any units. No. And on the right side, bam. So what am I going to do now? Divide by 2,000 kilograms on both sides. You'll notice that the kilograms cancel out. This is a 0 here. And 12,000 divided by 2,000 gives us a value of 6 meters per second. Now, one of the great things about these types of problems is it's pretty straightforward to look at your answer and determine if the answer makes sense. Well, let's think about it from the perspective of their original velocities. Which object had more momentum in the beginning? You'll notice the mass had a larger van. The van had a larger mass and a larger velocity. So it definitely had more momentum. And we saw that mathematically in this step right here where we calculated the momenta of the two objects. So you'll notice that my answer came out positive, meaning that the tangled mess of car, van, whatever you want to call it, is going to move in the direction that the van was moving originally. Why? Because the van had more momentum. In other words, the momentum of the car, which was negative, gets completely wiped out by the momentum of the van. But the van has an additional 12,000 meters per second worth of momentum. And of course, with the mass increased, since we have both objects together, larger mass moving with the momentum of 12,000 is definitely going to be going slower than the car was originally. Think about that. The car originally had a momentum of 12,000. Afterwards, the blob has a momentum of 12,000, but in the opposite direction. So in this case, when that momentum is divided up amongst a bigger mass, in this case 2,000 kilograms, we are going to get a smaller value for our velocity. All right, so that's what happens when two objects stick together. What happens when the objects bounce off of each other? So in this problem, we have a racquetball moving to the south at 5 meters per second, collides with a stationary billiard ball. I'm going to go ahead and make my racquetball blue because I feel like racquetballs are always blue. I don't think I've ever seen a racquetball any color other than blue. And then down here, I'm going to make my billiard ball an 8-ball, just because. Why not, right? It's the most famous of the billiard balls. I guess it's technically a pool ball if it's an 8-ball. Because in billiards, there are no pockets and no numbers. All right, so the 8-ball is at rest, and the racquetball is moving towards it to the south at 5 meters per second. We know that afterwards, the racquetball is going to bounce back to the north. So this is before over here. And on the right-hand side is going to be after. So after they collide, the racquetball is going to rebound, and it's now going to go to the north at 3 meters per second. And we want to figure out what is the 8-ball going to do. And here I am wasting your time while you wait for me to draw an 8-ball. A very poor one at that. All right, so we don't know what the 8-ball is going to do afterwards. That's our goal. So let's set up our equation. Mass racquetball times velocity of racquetball plus the mass of the billiard ball times the velocity equals the same exact thing, but with our little apostrophes on each of our velocities, showing that these are after the collision. Now, in this case, we can simplify the equation by eliminating the billiard ball prior to the collision. Why? Because it was stationary. In other words, it was at rest before that racquetball came along and hit it. So there's nothing else I can do to simplify this. I'm just going to go right to plugging in my values. So mass of the racquetball is 0.15 kilograms, and its initial velocity was 5 meters per second, but to the south. So I'm going to go ahead and just make south negative because that seems to be more intuitive. This term up here was 0, so I can just ignore it. On the right-hand side, we're dealing with the racquetball once again, but this time it's rebounding to the north, so positive, at 3 meters per second. And then we have the billiard ball with its mass of 0.35 kilograms times its unknown final velocity. Now, if you think about this, you might say, what direction is the billiard ball going to move? In this case, I hope that it would be very, very obvious based purely on Newton's laws of motion. We know that in order for the racquetball to bounce backward to the north, it has to experience a force pushing it to the north. And based on Newton's third law, it must therefore be pushing backwards on the 8-ball in the opposite direction, which would be to the south. So we definitely expect this 8-ball to be moving to the south. All right, so what do I get? Well, over here on the left-hand side, I have negative 0.75. Excuse me for leaving out my units temporarily. On the right-hand side, 0.45. And of course, 0.35 kilograms times my final billiard ball velocity. I'm going to subtract this guy from both sides of the equation. When I do that, I get negative 1.20. I'm going to put my units back in now, which is equal to 0.35 kilograms times this unknown velocity. And of course, now all I have to do is divide by 0.35 kilograms. Notice the kilograms will cancel. I will get meters per second as my answer, as the unit for my answer. And when I plug that into my calculator, I do get a value of negative 3.43 meters per second. But I'm going to leave off the negative, and I'm going to ask myself, what does that negative mean? Well, that negative, of course, means that it is to the south, as we predicted.